Here we want to go a little further and talk about our quantum state and fill in a few gaps here and there, tie up some loose ends, introduce some new concepts that we'll need later. And we return to postulate 1, that we have a vector in Hilbert space. Now, we talked about the dimensions of the Hilbert space corresponding to experimental outcomes in a particular basis. Now, as we see, and we'll look at this mostly through polarization, it is entirely possible that the state vector of an object is not in the same direction as one of those outcomes. It's somewhere in between. And this is a very important aspect of quantum mechanics. P.M. Dirac thought it was the most important distinction between classical physics and quantum mechanics. And here we want to emphasize it. Other people have other views, but it is a definite distinction. So let's go to polarization. Now, we use the H and V directions as our canonical basis. But we know we can always rotate either our polarizer or a polarizing beam splitter in a continuum of angles. There's a continuum of angles that we can measure in. And each of these is going to give two outcomes. Again, think of a polarizer, set it at some angle. It's either, the two outcomes would be it passes through or it doesn't pass through. That's a very simplistic way, not the way you'd actually do an experiment. With an experiment, you probably use a polarizing beam splitter where it goes through one channel or the other. But you always get two possible results. However, there's an infinity or continuum of ways you can measure because you can rotate it through 2 pi angles. Actually, it really only matters through not all of those, but let's not worry about that for the moment. And so, yes, again, that's what we just said. Now, let's consider a special case where it's 45 degrees in between. We should have discussed this before. But when we describe the state vector like this, we describe it as what we call a superposition of H and V. It's a mixture, equal mixture, if you will, of H and V. And again, that's because it's 45 degrees in between. If it's minus, there'll be a minus sign there. Pretty obvious. Now, in this case, one thing to note, though, is that this plus factor, in another basis, it is a possible outcome. And it's just that basis where you rotate it by 45 degrees, so it is one of the outcomes. But if you're measuring it not in that basis, then it is not one of those outcomes. And you're going to get probabilities. Here, of course, you're going to get 50-50 for H and V, so it splits them equally. But there are other examples that are a little more extreme, if you will. If we consider the infinite dimensional space a position. Now the Hilbert space is infinite dimensional. We're probably not going to say a whole lot about such Hilbert spaces, but they are dealt with in quantum mechanics. And there are some tricky aspects to going from a discrete or a finite dimensional Hilbert space to an infinite dimensional Hilbert space. Maybe we'll get into that, possibly not. But in this case, it is possible to have a superposition state. So you can have a state as follows. Then this is not going to be a realistic state, but it is in principle one you could have. It's allowable by the postulates or principles of quantum mechanics. And it simply consists of two positions. This would represent a particle that's equal probability to be at the position x equal 3 meters and x is equal to 42 meters. Now, you might say that's unphysical, but remember, we're not talking about the actual state of the particle. We're talking about the quantum state. The quantum state, it can reside, it has, again, a probability to be at 3 and a probability to be at 42. And again, such discrete position outcomes are a little bit artificial, but this is just to get the point across. But the thing to note is that this particular state is not a possible outcome of any measurement. So no matter what we do, in this particular case, we really won't have a quantum state. But it is states like this, these superpositions, that are important in what we've discussed already in terms of the double slit. So remember, the double slit, we can think of it as a superposition of the particle going through one slit or through the other. Slit 1, slit 2. That's a superposition state. And it's that superposition that's critical to get the interference pattern. So that's one of the important features of superpositions. It gives you interference patterns. Okay, let's go on. Another property of states that's important has to do with the mathematical nature of them. So when we say global phase factors, what do we mean by that? Well, we just mean if you can multiply by a factor that can be expressed as e to the I delta, where delta is some real constant, then if it multiplies the entire state, this just sits outside, it does not affect the probabilities. And we'll show this explicitly in a moment. But again, notice that e to the I delta can mean, that can express 1, minus 1, I, minus I. Those all can be expressed with appropriate factors of delta. And we'll show how that works now. So let's consider a general ket, and we'll have this global phase factor out front. We'll have A alpha minus B beta, where A and B could be complex coefficients. We're not going to really be concerned with those. But we want to find the probability to find the outcome omega. So recall we did discuss how to do this before. We express this as follows, is that we take the bra vector now of what the outcome we're interested in and act on the state and take the modulus square. Writing this out, we see the following. Well, remember the modulus square just says we're taking the complex conjugate times itself. And notice when we do that, this factor, we get e to the minus I delta for the first term, and we get e to the I delta for the second term. In that case, we see that, well, we get this, which means that we get the same probability whether that e to the I delta is there or not. It doesn't matter. So really that e to the I delta doesn't affect the probability at all. It doesn't change it. Because it cancels, because you're taking the modulus square. And the modulus square of e to the I something is 1. Now this is going to be useful because we're going to be able to simplify states. We're going to use this once or twice here. But let's take a look at this particular state here I just made up randomly. I alpha minus e to the I gamma beta. Okay, that seems arbitrary, but you can actually write this seemingly, well, it is a simpler case, but a simpler way, but it may not seem like it. But notice as follows. If I factor out the I from both, I'm going to have a minus I here multiplying this, because I times minus I gives us 1. And then I can express minus I as e to the I minus pi over 2. So I just combine them there. And notice what I've done is I've taken factored out the I, and written it this way. And that means for this particular state, I don't need to keep that I in front because it's not doing anything. If we're talking about, if this is the only state we're talking about, and we're talking about probabilities of this state only. That's it. So, but of course, like I said, if the global phase factors can be ignored, but relative phase factors are important. So, for example, a relative phase factor would be this minus sign. Minus 1 can be expressed as a phase. Those are important when you consider other cases, especially when it's interacting with other objects. Okay. Next topic is multi-particle states. So up to now we talked about single, say, photons with polarization or polarization of a single photon. What if we have 2 objects? Or n objects, but you'll see once we go to 2, it's pretty clear how to generalize this to general n. Finite n, that is. So let's take Alice and Bob, and they each have a photon, and we want to represent the polarization state of each. Or not of each, but we want it combined as well. Well, again, the photon that Alice has, again, that's sent to Alice, it's represented with two-dimensional Hilbert space, as we said, and we're going to call that H sub A. And Bob's also going to have a two-dimensional Hilbert space, which we'll call H sub B. And again, within each space, there's a state vector, you can think of it, that represents the polarization state for those 2 photons. But how do we represent this now as a single system? And this is the important thing. And so again, here we have the state, we're just saying, say Alice is in the state H, Bob's in the state V, and they reside in their own Hilbert space. But this is not the most general way to express this in quantum mechanics, and indeed we need to be careful with this, because we want to consider it as a single system. Now we're considering the 2 photons and nothing else. So we need the joint quantum state, if you will, of Alice and Bob's photon, each photon. Now the way this is done is through what's called a tensor product state. And it may sound and look a little intimidating, but it's actually rather easy once you start getting used to it. Just takes a little bit of getting used to. Now, the way we're going to write it is with this O with a cross in it. That's sometimes called the tensor product. And this will be the two vectors, and they'll be tensored together is a kind of way sometimes it's said. And they'll reside in the tensored product space, Hilbert space, of HA and HB. Now, we need to kind of get into this, what we actually mean by this. So actually, this is kind of the formal mathematical way that we should always represent, but we're not. We're lazy physicists. We're going to simplify this notation, especially once we get into writing a lot of kets. We're going to write it in various ways, and we're going to write it as is most convenient for the time we're doing. So first of all, this is the full, most specific way to write it, the most proper way, if you will. Sometimes we'll write it as this, HA times HV, without just removing that O times, because we don't want to write that cross symbol all the time. Also, this one is going to be more, is that now we're going to remove the labels, but it is understood that whenever we write the two kets like this, the first ket refers to Alice and the second one refers to Bob, so we have to be careful with our algebra to make sure that Alice's is first, Bob's second. Likewise, we can all put in the single ket if we want, where again, the first entry is Alice's, the second is in Bob's. And that's a change. So let's look at the properties of this tensor product next. Now, as we proceed and work with these product states, it will become clear how they work. But right now we want to lay out the rules of the tensor product, and this will help us go along. And as we do examples, it should become more clear how this works, and eventually hopefully we'll become very comfortable with working with such. And again, these multi-particle states are extremely important if you want to understand the fun aspects of quantum mechanics, or the foundations, if you will. But first of all, let's look at scalar multiplication. So here we have lambda as a scalar. If we have, and again, I could use the O times in here, the symbol, but I'm going to kind of not for this purpose here. It should be understood from the previous slide that if we're considering, say, Alice and Bob, the first vector is Alice, the second one's Bob, continuing. And in this case, a scalar, you can multiply it, you can distribute it one way or the other, of course. There's only going to be one factor of lambda on the other side, but you can multiply by u, or you can multiply it by v, but not both, of course. Or if you want to split it in half and do it, whatever. Square root it, I should say. Take the square root of lambda and multiply by both, you may. Distributed v, if we have two vectors. Now notice how this works. This is where you have to kind of pay attention. These two, u and v, lie in the same Hilbert space. Those are both Alice's, if you will. Superposition in Alice's. This one will be Bob, and you can distribute it as such. So you got to keep track of the order there. So sometimes you have to look at the algebra to do that. The inner product, this is an important part. How do we take care of an inner product? Well, again, let's say we have uv and u prime v prime. Then when we take the inner product uv on u prime v prime, we take the first two elements and form that inner product. So that's going to be u on u prime. We'll take the second entry, v on v prime. And you can see how that would generalize to n particles. You just kind of tag them along as well. Lastly, the dimension of the product, the Hilbert product space, is the product of the dimensions of the subspace. So what we're going to be concerned with are two-dimensional Hilbert spaces for, say, polarization. When we look at two photons, we're going to have four-dimensional. And that's what we want to look at next, is look at two photons, but examine their polarization. And let's do it so they're both in the HV bases, just to start with. In this case, if we measure in the HV bases, we have four possible outcomes of these photons in polarization. Again, we're measuring their polarization. These are the only possible outcomes we can have in that basis. And as we said, if those are all the possible outcomes when measured in this basis, they would form the dimensions of our Hilbert space. And we need to check if that is consistent with what we've said so far. So the question is, do the corresponding state factors to each outcome, HH, HV, BH, and VV, do they form a basis? How do we check? Well, first of all, remember they need to be orthonormal. So let's go through here and check this. We'll do this in explicit detail. We won't go through all of them because it should be pretty clear once we see one work, how the others work. But let's take HH on HH. Remember, we take the first entries, take their inner product, and the second entries. Those are both 1 because we understand that H and V themselves are orthonormal. Same with V. Even if we do the cross ones, so here we have H on H and then V on V because that's the second one. And lastly, we want to check, so they're normalized. What about orthogonality? We'll just do a couple of these. There's several to do, but we'll just do a couple of these. So HH on VV, well, remember, the first entry, so that's H on V, that's already 0. Here, even HH on HV, well, the first one is H on H, but the second one's H on V, which vanishes. So they are orthonormal. So that's half it. The other part we need to check is, do they span the space? And here, I'm going to say it without proof. They do span the space, and you could try to think. It should be obvious that if you take the 2 photons separately that are in HV bases, no combination of those are going to be able to come out of that. There's going to be no combination that's not going to be expressed as a combination of these. But we'll just state that without proof. And again, so there's several like homework exercises to get familiar with this, is to show that, for example, this basis here, H plus H minus, V plus V minus, that does form a basis. However, H plus H minus, VR, VL does not. You might think about it, you might know, it might be obvious already off the top of your head, why not? And again, to do this, you need to check these 2 things. Primarily, we'll check the first is going to be really the case. It's going to be important. Okay, let's move on. Okay, now let's look at this, and we want to use these multi-particle states, to look at something else that's interesting here, interesting feature. But let's take a state now, H minus. Now again, this is a product state. It's not meant to mean H negative 8. It's just like H minus. So Alice has H, Bob has minus, say, for example. And we'll look at the following probability that Alice measures minus when measured in the basis. So, and Bob measures V when it's in this state H minus. They might say that's 0. Well, let's think of it. You got to go slowly here. So remember how we do this. We take the outcome we're interested in, which is minus V, and we make the bra there, and we act on the state it's in, which is H minus. That. Now again, here we need to be, again, just got to be careful here of which bra corresponds to which ket. Again, so again, this was the minus is associated with Alice, the H is associated with Alice. So we want to pull the minus on the H and then the V on that second minus there. Like that. And that should look like that, which we can express as follows. Now notice that the modulus square of a product is the product of the modulus squares. That should be obvious. But the takeaway here is that, well, notice that now we have 2 separate modulus square here. So we're really just finding the probability that minus is in finding outcome minus when in H state multiplied by the probability V in minus. But recall in the discussion of probability what that means. That means the joint probability here factorizes, thus they are independent. So that's the definition of independence, is if the joint probabilities factorize. Okay, let's look at another example. So let's take the state, I'm going to call it psi minus. We'll see why, but that's just it is a way we label this particular state. HV minus VH over square root of 2. The square root of 2, remember, is a normalization factor. So now that makes that this state vector is normalized. So whenever you have 2 terms there in a superposition, you almost, well, it depends on what the coefficients are, but if there's no real coefficients there, square root of 2 will be present often. But this also says that these are equally likely outcomes. Okay, but we want to find the probability now. Let's consider this one here, that Alice measures plus, Bob measures minus when it's in this state, psi minus. So we do it again. The bra is probably the outcome we're trying to find, plus minus, and then this is the state. I factored out the 1 over square root of 2 and squared it just to make life easy. Okay, now we go ahead and distribute that out. We get these two terms. But notice now, we cannot factorize this. There's no way to write this as two separate probabilities, one for Alice's side and one for Bob, or one for Alice's measurement and one for Bob's measurement. It's just not possible. So it means that, well, the probabilities are not independent. That's one conclusion you can say. But such a state is called an entangled state. And it's going to be true that if the state vector can be factorized, like up on top here, that's clearly factorizable, then the probabilities are going to be factorizable. That should be hopefully almost obvious. But if the state vector is not factorizable, then the probability again will not be factorizable, and thus the independence is no longer there. Now, this is a critical, really kind of new aspect of quantum mechanics, I would say, and one probably the most significant if you want to talk about the mysteries of quantum mechanics, if you will. And let's think about this a little more carefully. So if we measured this state, let's just consider this state alone, not the particular measurement, this state here, and we measured in the HV bases, when the first person measures the outcome, then the probabilities change for that person. So let's just do an example. Let's say that Alice measures and she gets a V. If she gets a V, then it's a V with probability 1. And this is no longer a possible state, so the state collapses to this pair here. But what that does is it determines the photon that Bob has as being H. Prior to the first measurement, you cannot think of them independently. They're in this quantum state. But it's when that first measurement is made, you break the entanglement, it's called, and you get one of these two results. And again, it could be more. There could be more terms here. Two is really enough for us to understand the nature of this. Now, why is this interesting or significant? Well, notice there's nothing in this discussion that talks about where these photons are or where Alice and Bob are. That's not in this story. It's not being described here. So they can be arbitrarily far apart. They can be in different galaxies. But somehow, when Alice measures hers and she gets a V, at that instant of time, Bob's is determined to be an H. The state changes. And it has to, because if it doesn't, then there's a probability that Bob might measure a V as well, and that would say this is not a complete description of the state because there is no outcome VV in the state. That probability is 0 as given by this. But somehow, they both measured V. So when the first person does a measurement, it reduces it to one of the subterms in the entangled, or a single element in the superposition. And we'll hopefully come back and return to this because that's where the interesting aspects of quantum mechanics come into play. Okay, along these lines, these entangled states, is what's called the Bell basis. And we just introduced it here, you may have seen it in your texts or wherever. And there are just 4 state vectors that we can express as a basis in the product Hilbert space of 2 photons in terms of the polarization. And again, you can kind of see how they're made. So the psi refers to opposite outcomes. Plus means a plus between them. Minus means a minus, and so on with the other ones. It's the phi states have the same in each ket, and the plus and minus that. Now, you might be inclined to think that these two are essentially the same because the kets are the same. You got to be careful with that because one thing you want to check, are they orthogonal or not? And if they're orthogonal, they correspond to two separate outcomes, mutually exclusive outcomes in a particular basis. So you can quickly check that these are orthogonal. Let's do this real quickly. If you just now do this in your head, turn this psi plus into a bra. There's no i's here, so you don't have to worry about complex conjugation. And then you act on it, distribute this around. You get HV on HG is 1. These are orthogonal, so HV on VH gives you 0. And lastly, you have minus VH on VH, which gives you minus 1. So you have 1 minus 1 is 0. So these are clearly orthogonal. These are clearly orthogonal. It might take a little bit more effort to show that these, for example, are orthogonal, but it can be done just by, I would recommend doing it right now. Pause the lecture and just do it on a piece of paper really quick. We don't care about the square roots of 2 or much, just want to check orthogonality. And it's clear that these are all normalized because they have 1 over square root of 2, and the coefficients are all modulus 1. And again, we'll return to these bases later. Here, just showing it as an example. But it will be an exercise to show that this does form a basis. We did much of the work if you just did what I asked you to do. Okay. Lastly, let's look at the column vector representation. So remember, we talked about if we choose what we call the canonical basis HV, where H is 1, 0 and V is 0, 1, then we can express our bra and ket vectors out, and so on. And we have these three bases here, the plus minus and the RL bases, the circular polarized ones. There. The question is, how do you express the tensor product states if you have those? Well, let's just go through this generally, and then we show explicitly for the HV, and we'll do had homework on the other ones. But first of all, if you're given two column vectors, we only care about 2. So we have A is equal to A1, A2, and B is equal to B2. Then the tensor product of those two, which we can just call AB. That A is not supposed to be there. Let me just cross that out. I don't know how that got in there. But it's just going to be, you can think of it as follows. You're going to have a copy of the B vector, then multiply by A1, and that's going to take 2 slots. And then you have A2 on the lower slots times B1, B2. And so it just distributes like that. So this is what we call the tensor product version of it. And of course, we're going from 2 to 4. As we said, the dimension is 4-dimensional now. So if you look now, go back to our H and V, it's pretty simple to check, just by going through this prescription here, what those are. And they're very simple. This is why it's canonical basis. It's just 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Those are our basis kets in this canonical basis, if you will. And again, one exercise will be show what these column vectors look like in the Bell basis. That's another question. What do those vectors look like? So there's many questions we can ask around it. And get just for practice in getting used to this combination like here. It's actually relatively straightforward once you get the hang of it. Lastly, so footnote, we're going to need to go on beyond state vectors, and we'll, as column and row vectors, we'll need to talk about matrices. They'll be operators. We'll get into that shortly. But when we talk about such case, we're also going to be taking tensor products of operators. And how does that work in this format here? Well, if we're expressing the operators on some basis, they'll be expressed as matrices as follows. So A1, again, row column for the subscripts. B1, B1, B2, B2, 2. The tensor product, again, is the same idea as up here. We just take A11 times the B matrix, as you can kind of see that's shown here. A12 times the B matrix, A21 times the B matrix, and A22 times the B matrix. Note, though, it's the order of the product is important, obviously, because this is Alice's and that's Bob's. So we don't want to swap them. We don't want to attribute operations that Bob does on his photon to Alice's photon. That would make sense. So the order does matter, and you can see that would change the representation of the matrix as well. So we do need to be a little bit careful about the order there. Okay, so this is to fill in a little bit about the first postulate in the quantum state. We'll go on now and start talking about operators and the significance of them within quantum mechanics.